Hello, good afternoon, everyone. This is the live session related to NPTEL MOOC on Engineering Hydrology. Myself, Sreeja Pekkat. I think by this time we have completed around 4 weeks, 4 weeks of lectures. And regarding that, whatever doubts are there from the students who have registered in this particular course, you can come and ask. So this particular course is on engineering hydrology. So I hope you have gone through 4 weeks lectures. The subject engineering hydrology is basically for the UG engineering BTech students, those who are doing BTech in civil engineering and also related areas. So this particular subject is related to the engineering hydrology is mainly we are talking about the divisions, what is water which is present in the atmosphere, surface and subsurface. So till now we have completed atmospheric hydrology. We have started with the introductory preliminary concepts, and after that we have directly moved on to the atmospheric hydrology. Now from next week onwards it will be on subsurface hydrology. So the water, everybody, as of now, when we talk about hydrology, even a small kid knows about rainfall. So rainfall is very much familiar to everyone, and also the surface water is very much familiar because whenever the rainfall is occurring, some amount of water which is coming after losses, some of the losses, it will be flowing on the ground surface. That is termed as the surface runoff, which is a contribution to the water which is present in the on the surface, that is in the rivers, lakes, water bodies, etc. So regarding the water which is getting evaporated into the atmosphere, the study related to that we have covered under atmospheric water. So regarding water vapor dynamics and how the water vapor is formed from the surface water, the process related to evaporation, evapotranspiration, all these things we have covered. And some of the numerical examples also we have solved, which are very much required for understanding the concepts. So water vapor dynamics, when we were talking about, we were making use of the basics physics we have learned in our school days. So very fundamentals related to that we have utilized. And then we were talking about, we have utilized that and we have gone for the understanding related to temperature variation, pressure variation, etc. in the atmosphere. So some yes, good afternoon, Satish. Do you have any doubts? If you have any doubts, you can put it there and I can read out and clear it. This is the doubt clearing session related to engineering hydrology course. I don't know whether you have registered in this particular course. If you have registered in the course and if you have gone through the lectures till 4th week, any doubts regarding the lecture, please clear it now. So I'll continue with my discussion. That is, we were talking about the variation of temperature, pressure in the atmosphere. We have found out by using the basic knowledge from physics. For understanding the variation of pressure and temperature in the atmosphere, we have made use of two basic laws, that is ideal gas law and hydrostatic pressure law. So by making use of these two laws, we have derived the equation for finding out the pressure at a particular location at a certain height from the ground surface or at an altitude in the atmosphere by knowing the pressure at the ground level or at some other lower level. So from the expression we have seen, we know already as the altitude increases, the temperature and pressure decreases. So how this variation as we move into the atmosphere, those things we have covered in the lecture. After that, we have moved on to the derivation of expressions regarding the evaporation, different hydrologic processes such as evaporation, evapotranspiration, etc. For that, we were making use of the Reynolds transport theorem. Reynolds transport theorem was making use of the principle which is used in our course engineering hydrology, making use of the Eulerian principle. It is relating the system concepts to the control volume concept. So I'm coming back to Reynolds transport theorem. Reynolds transport theorem relates the system concepts to the control volume concept. So our analysis is based on RTT, and by making use of Reynolds transport principles theorem, we have derived the equations related to evaporation and different methods of experimental measurement of evaporation, empirical methods to find out evaporation. All these we have seen in the lectures. And some examples related to those aspects also covered, numerical examples for understanding how these equations can be utilized for finding out the evaporation. And also evapotranspiration, some example, I think one example we have solved. And regarding those assignments also we have put up. So if anybody is having doubt related to that, they can post their queries and I'll be able to answer to that. In case you are not able to post it now, you please send email to me or through the NPTEL email which is given to you, so that time to time we'll be clearing your doubts. And in detail, if I talk about evaporation by making use of energy balance method, then coming to the aerodynamic method, and after that a combination method is also studied. Example is Priestley-Taylor method. So by making use of all these equations, we can compute evaporation. Measurements related to evaporation includes evaporation pans, different types of pans we have seen, and an important terminology related to pan coefficient we have seen while computing the evaporation from a water body if we are having the pan evaporation. Then after that, we have moved on to the process precipitation. Precipitation, mainly we were discussing about rainfall. Different types of precipitation we have discussed. Then in detail, topic related to rainfall we have covered. And how to measure rainfall that we have seen. That is, everyone knows rain gauges are utilized. Two types of rain gauges, recording and non-recording rain gauges. And nowadays, for us in India, IMD is installing automatic rain gauges, automatic weather stations at different locations, and we are having good network of automatic weather stations from which we'll be able to get the rainfall data. Time to time rainfall data, very short interval rainfall data also can be obtained. But in the case of recording type, non-recording type rain gauges, it is manual recording type of rain gauges. We have to measure it, as I have mentioned, explained in the lecture. It will be from 8 a.m. to next day 8 a.m., 24 hours gap, or during rainy days, the frequency of measurement will be more. But nowadays, we are having very good automatic rain gauges in which we don't have to measure manually. Automatically, it will be obtained in the computer. And after getting the rainfall data, we have seen how to get the average rainfall at a particular location. So those average rainfall computation by using different methods we have seen in the lectures, and some of the numerical examples also we have solved related to that. Once the rainfall related topic is over, we have moved on to the computation, or we have to move on to the subsurface water evaporation, water getting evaporated into the atmosphere. Atmospheric water we have quantified in, and after that cloud formation, mechanism behind the cloud formation we have seen. Then due to condensation we were obtaining different types of precipitation. Out of that, rainfall in detail, average rainfall, if there is any data missing, how to find out the missing rainfall, and the type of representation of rainfall by means of hydrograph, mass curve, all these things we have covered in detail. Now, in the coming lecture onwards, we'll be moving on to the subsurface hydrology. Once the rainfall is occurring on the ground surface, so many losses are taking place. Different hydrologic processes you have studied: evaporation, evapotranspiration, infiltration, runoff. This way, different processes are classified. And precipitation, evaporation, evapotranspiration, all these we have covered in the previous 4 weeks lectures. Now we will be moving on to subsurface, in which we'll be discussing about the water which is infiltrated into the ground. Into the ground, how much it is represented by means of the hydrologic process that is known as infiltration. Regarding different hydrologic processes, we will be expressing the theory behind it, different ways of estimating that, empirical methods, experimental methods, theoretical methods. So in detail regarding atmospheric hydrology completed, including the problem solving session. And after that, next week onwards, we'll be moving on to subsurface hydrology. It's also very important when we talk about the contribution of water from subsurface, unsaturated region to saturated region, or to groundwater is concerned. In this particular course, we'll be dealing with the subsurface water which is present in the unsaturated region, not in the saturated region. Saturated region we'll be studying in a separate course termed as groundwater hydrology. In this engineering hydrology, we are dealing with only in this particular course, I am discussing only related to the water which is present in the unsaturated region. And once that subsurface water in the unsaturated region completed, we will move on to saturated water. All these topics are very important as far as these competitive examinations are concerned, and the fundamentals related to hydrology is very important when we talk about the study about hydrologic extremes. So here in this case, hydrologic extremes, very fundamental way, minimal way we'll be covering. That will be in the last 2 weeks, hydrologic statistics and hydrology design. But very minimal requirements only will be covering, but those fundamental knowledge is required for carrying out research, advancing in the particular area, climate related studies, climate change related studies, urban heat, urban flood. All these things requires the fundamental knowledge about this particular subject. So different hydrologic processes need to be clearly understood. So that way, if there is any doubt related to this particular subject, till now, whatever we have covered, those students who have registered in this particular course will be able to, if you are facing any issue related to the topic, you are always welcome to clear the doubts. Because this particular course is designed in such a way that in-depth explanation about the topics which are prescribed in the syllabus is carried out. So any doubt related to those, that is initially when we were talking about RTT, after derivation of Reynolds transport theorem, we have derived the fundamental equations, mass conservation, momentum conservation, and energy conservation equations. And this mass balance equation, momentum conservation equation, all these are very important when we talk about rainfall runoff modeling. When it comes to a river flow, when it comes to a pipe flow, transient analysis, in all these cases, we'll be making use of these fundamental principles. So those fundamental equations can be derived using in Reynolds transport theorem. So those equations which we have derived are related to hydrology course. The theorem can be extended to any problem related to flow of fluid. It can be gas, it can be liquid. So the basics related to this particular subject we have covered. Fundamental introductory lectures. That is in the, I think in the first week of the lecture itself, we were covering entire basics, fundamental requirements related to the course. After that, we were considering one by one atmospheric water in depth we have covered. Now, subsurface, surface. After that, we'll move on to the application of these processes which you have studied, theoretical knowledge which you have gained in these week's lectures. We'll be moving on to the hydrologic statistics and design. Very minimal way, we'll be looking into those aspects. So, since I think those students who are enrolled are not present over here. And there was one particular query related to thunderstorm cell model. In that particular equation, we were using thunderstorm cell. Let me introduce that. Thunderstorm cell is utilized to find out the rainfall intensity. So in that, we were having some particular term related to QV1 and QV2, that is specific humidity at section 1 and section 2. That is inflow region, outflow region is there. The numerical example which we have solved in the during the lecture session, we were having QV1 and QV2 tabular form we have made, and from that there was a query from one of the candidate asking about why QV1 is taken as the average of section 1 and section 2. Cloud base is given at a certain depth, said cloud base is there. inlet region is extending from the ground surface to the cloud base. So we won't be able to get the exact variation of these QV1, how it is varying from ground surface to the cloud base, which is representing the inflow region. That is why we were taking the average value by computing the specific humidity at section 1 and section 2. As far as upper part is considered, outlet region is considered. We are considering the upper level, I think it is 9.5 kilometers, and corresponding to that specific humidity is required. That we have utilized, but when we talk about the inflow region, we have to consider the variation. So that variation is not there with us. So we are considering the average value of the specific humidity. So here I am winding up this session. Other than that, no more questions were there in the Gmail group also. So in case any more doubts are there, please send email to us. We'll be replying to you on time. So next week onwards, we'll be moving on to the subsurface water hydrology lectures. So please go through that and clear your, update your knowledge related to this particular subject. And any doubts or any clarification required related to this particular topic, please post your doubts in the NPTEL Gmail or to me in personal email ID. Thank you very much. Here I am winding up this live session. Thank you all. Sunita? Nobody is there. I have given the brief introduction and now we can wind up. Okay. Whichever questions they have asked through email, that also I have cleared. So I think no more things are there to clarify. Okay. Okay? Okay. Okay.